Where do I find the fastest ray tracing software?
So, an introduction to FREDmpc. So, officially released at the beginning of 2019, FREDmpc is the only general-purpose optical engineering software in the world that performs the ray trace on the GPU board. And this results in a speed increase of 100 to 500 times higher than that of conventional multi-threaded CPU ray trace softwares. You can see there's a small asterisk by the 500. This is a ballpark figure because technically it's unlimited, and we'll talk about that later on in the presentation. MPC, a lot of people ask what MPC stands for, and it stands for massively parallel computing, which is what the GPUs are for. So the first question to ask is, why did Photon Engineering create FREDmpc? Well, that's because many FRED users over the last few years have begun to need to simulate larger and larger models and trace billions and billions of rays for accurate stray light analysis or design of illumination systems. So over the last few years, Photon Engineering has been addressing this trend. A few years ago, they allowed FRED to be run on a distributed calculation environment. In other words, connecting multiple PCs together and sharing the calculation among them. Also, internally in the system, there was a lot of rewrite of the software code to switch the ray counter from a large to a huge. Sorry, a long to a huge. Essentially removing the limit of 2 billion rays, which was the limit up until 2016, I think. And now changing that to a huge essentially allows you to trace up to almost an infinite amount of rays in a FRED simulation. And then also to handle large models in the user interface, making sure that the tessellation, the view, the manipulation of the model is multi-threaded tessellation. Therefore, a smoother response when you're moving the model in the 3D view. So all of these developments improve the usability of the software to handle large models and large ray traces, but they're all dependent on the CPU architecture, which is relatively slow to evolve going forward. So it's only incremental improvements. So it was time to move to GPUs. And the diagrams at the bottom here just show you the evolution of FRED. So in 2001, when FRED was first released, version 1, it was actually a single-threaded CPU ray trace. And then 5 years later, for version 5 or 6, it became a multi-threaded CPU ray trace. Then in 2017, you were able to do the FRED calculation on a cluster, essentially distributed computing. And then finally, at the beginning of 2019, being able to do the GPU ray tracing.
Tom, sorry for interrupting you. And I really often get this question, what is the meaning really of this distributed computing cluster? Is this on your own computer, or you can use more computers?
Yeah, you can connect multiple computers on the same network. So separate computers, just all connected together. And when you do a FRED calculation, it divides up the calculation among all the computers and then brings the results back together. So if, for example, you wanted to do a 10 billion ray trace calculation and you have 10 computers, FRED will automatically, in a simple case, give 1 billion rays to each computer to do the 1 billion rays ray trace, and then accumulate the results and bring them back, the result back to the head computer, if you will.
Does each computer need a FRED license for this?
No, you only need one license for what's called the controller or the head computer. And then you can connect as many computers as you wish on your local network. And that's unlimited. It depends on how many you have available, I guess. So that's really beneficial because it's you can scale it as large as you need. But the GPUs are much more powerful because they scale much quicker. A GPU board can have hundreds of CPU cores, the equivalent of hundreds of cores per GPU board, which is a lot quicker to scale than connecting 10 computers with 8 cores each, for example. So the distributed computing is a nice, it was essentially 2 years ago, it was a stopgap development while the development team was working on the GPU ray tracing. However, it's still very useful because you can use the GPU ray tracing on a distributed computing cluster. So you can have multiple computers, each using the GPU boards as well. So we can combine both technologies for a much faster ray trace. So talking about GPUs. So the GPU hardware technology, of which NVIDIA is an industry leader, allows for thousands of processing units, as I just mentioned, running in parallel within a single workstation or computer. And essentially what happens on the GPU board is that the numerical problem is broken into small chunks and operated on in parallel by multiple processors. So these types of calculations must be able to be broken up into chunks or small batches to share among the many cores of a GPU board. And ray tracing is quite suitable for that because what we're doing here is just breaking up the number of rays that we're tracing on each of the processors of the GPU. So, you know, each GPU core gets, you know, a certain number of rays and traces them, and they all trace parallel to each other, and then the results are combined. The nice thing about GPU hardware and software is that it's rapidly advancing and it's highly scalable, and is also, relatively speaking, it's quite cheap to upgrade a GPU board or insert another GPU board into your workstation. So by simply adding or upgrading the GPU board in a PC, the ray tracing and calculations of FREDmpc can be performed orders of magnitude faster using GPUs than conventional multi-threaded CPUs. That's the real benefit. So Proton Engineering, this back in 2017, started talking to NVIDIA and working with NVIDIA to understand how to translate the ray tracing to the GPU language. As you might already know, GPU can also do ray tracing, generally speaking, and it's used in a lot of special effects for films and computer games. But it's not quite the same type of ray tracing as what we need for engineering or scientific analysis. It doesn't have the ability to have accurate scatter models, extremely accurate surface representations, which might be critical for our optical problems. So it wasn't just a straightforward conversion from what we have in the FRED code, which is C++ programming language, to convert to the CUDA code of the GPUs. Unfortunately, it meant, because they were so different in the languages, and this type of detail in the ray tracing was required, there was no quick translation. Every FRED feature that needed to be run on the GPUs had to be completely rewritten from scratch in the GPU code. So the development team just had a long list of things they just need to translate one by one into the CUDA code. And there was no shortcut to doing this. This took a couple of years. And is probably the reason why no other larger ray trace software, i.e. our competitors, have done this yet. It's just a huge job. So now, inside FREDmpc, there are two versions of the code. So any feature that is supported on the GPUs has been written both in C++ for the CPU version, if you will, and then the GPU version as well, for when we want to run it on the GPUs. So for example, when the user requests to run the calculation on the GPUs, the FRED model has to pass through a translator to represent itself on the GPU code before we can actually do the ray trace. And this is all done behind the scenes, but it's just important to highlight that every feature in FRED now has two versions of the code for CPUs and GPUs. So for users who might be considering whether or not their current workstation where they're running FRED might be suitable for FREDmpc, there's two key points you need to do if you want to check your GPU board. First of all, it must be an NVIDIA GPU board. FREDmpc only works with NVIDIA. And also, the GPU board must have what's called a compute capability greater than 0. Essentially, it just means it has to be relatively modern over the last few years, because most modern GPU boards now have a value of 5 or higher. But if you want to check this yourself, you need to run FRED, and then in the command line at the bottom, write CUDA info non-VML, and you'll get a report telling you whether FRED can see and use the GPU board. The example at the top is printed to the output window, and this is the fail case, telling you NVIDIA board not found or has insufficient compute capability. Okay, and then in the success case, it'll tell you FREDmpc device count 1, so it's found one GPU board it can use for FREDmpc, and it has a compute capability of 5.0, for example. So if you see that straight away, you understand that you can use FREDmpc on your computer with this GPU board.
Tom, maybe one question. If I see here device 1 count 1, can I use more than one graphic card?
Yes.
For the wow.
Yeah. So you can have as many graphic cards as you can fit inside your workstation. And they'll be listed here, device count 2, 3, 4, and then each one it will list, and you see here the line 12, compute device number 0. So that's the first one, and then the next one will be device number 1, device number 2, and so on. And there's no limit to this. It just depends on the hardware, whether you can install the GPU boards. But if you have them installed, FRED can use them for the calculation. So when do we want to use FREDmpc? I know the answer is obvious, because we want a faster calculation. But specifically, it's really beneficial if we need to trace large number of rays. So, and the reason why I say a large number of rays is because there's a little bit of overhead time. When you're doing a calculation on the GPU, there's some initial preparations that FRED needs to make. And for example, this might take 40 seconds or a minute or 30 seconds, something like that. So if you're only tracing a small number of rays, it's quicker to do it on the CPUs. If it's only going to take 1 minute on the CPUs, it's, there's no benefit to doing it on the GPU. So the real advantage is when you're tracing many, many rays, so tens of millions, hundreds of millions, billions, those sorts of numbers. And the rule of thumb that I go by is if you're often tracing tens of millions of rays or waiting, an hour, 2 hours, 12 hours, 24 hours, something like that, then FREDmpc can be very valuable for you. If you're just doing ray traces that just take 1 or 2 minutes, there's no benefit that you'll see. And then the second case is for large models. So when you have thousands and thousands of surfaces or components in your model, one advantage that we've seen with the GPUs over the CPUs is that during the ray trace, the GPU is very, very fast at sorting through all of the possible surfaces in the geometry to understand which one the ray hits next when it's traveling through the system. So if you have models that contain thousands of geometry elements, you know, for example, large imported CAD files, then the GPUs will perform very, very well compared to the CPUs.
Tom, one question. Which applications do you have in mind? What will fit or will be very good for FREDmpc? Which application you see? I mean, you have long years of experience. What do you think is demanding?
Well, the main advantage is that when you need to trace so many rays, because you're tracing very small power values, or you need very accurate statistics, and you need to trace billions of rays, then FREDmpc is so valuable. So stray light analysis is the obvious one, and that is a big part of the FRED user base. But also illumination applications too, which also require millions and millions or billions of rays to get nice, accurate illumination profiles. So those two applications immediately come to mind. But anything that has large number of surfaces, large optical models that just require billions of rays, because rays are bouncing around everywhere, lots of scattering, lots of ghosting between optical surfaces, things like that are where FREDmpc does very well. So one thing that sometimes the FRED users are not too clear, if they haven't looked at FREDmpc yet, is how is it different to the usual version of FRED? Honestly, it's almost identical. The user interface is exactly the same. The tree, the way you set up the model or import models, set up optical properties. You also have the CPU ray trace buttons, which have been used until now. But also for FREDmpc, we have 3 extra buttons. And that's essentially what FREDmpc is. It allows you the ability to switch to doing the ray trace on the GPUs. That's what these buttons are. And I'll explain the 3 in the next slide. But everything else, in terms of how you use FREDmpc, is exactly the same. But now you have the option to do the GPU ray tracing. Of course, when it's a model that's not suitable for GPU ray tracing, like a very quick ray trace, you can do the CPU ray trace with in the usual way with the usual buttons. So just to highlight the 3 buttons here, just to explain what they are and the differences. So I'm going to start with the middle one, and it's maybe a little bit difficult to see the icons here. But what we have in the words here, MPC going down, and we got rays coming out to the right. And then the button on the left side actually has additional blue dots representing a source. Okay. So let's talk about this one first. It's called MPC traced GPU rays. A little bit confusing at the start. What does that mean? Think of it, I like to call it the full GPU ray trace. To call it the full GPU ray trace, and it becomes a little bit more obvious. When you click this button, the sources are generated on the GPU, the ray trace is done on the GPU, and the analyses such as, for example, calculating the irradiance is also done on the GPU. Everything is done on the GPU. Nothing is done on the CPU. Nothing is held in the computer memory, the RAM or virtual memory of the hard disk. Everything is done on the GPU. That's why we call it the full GPU ray traced. And then the button on the left here with the blue dots representing the source is what I call the hybrid GPU-CPU ray trace. This is slightly different. In this case, the source is created on the CPU in the usual way. Then the rays are transferred to the GPU in batches. They're being ray traced through the system on the GPU. And then the results, the rays themselves in their final location, are brought back to the RAM on the CPU. And then the analyses or post-processing is done on the CPU. Okay. Because there's a lot more flexibility if you have the rays at the end of the ray trace in your RAM or virtual memory, that you do post-processing using your own scripting or other types of analyses. So you have much more freedom if they remain in the RAM in that case. So there's a second option there. And then the third button is MPC Trace Advanced. It brings up an advanced settings window. For FRED users listening, it's very similar in concept to the FRED's advanced ray trace dialog. It allows a few customized options, such as if you want to keep track of the ray trace paths, generate a log file if you want to check for errors, and you can do some settings in terms of how much memory the GPU is being allocated for the ray trace and so on. Little sort of adjustments for the ray trace if you need to improve things or there are some problems you need to get around.
Tom, one thing comes into my mind. I mean, there are special applications to just only use the full GPU ray trace, or there are some examples where I should use the hybrid use.
Yeah.
Do you have something in mind? I think it's great that FRED allows you to, to say which boards you're using, but
yeah, sure. Okay, so the general reason why there's two is because the development team, the programmers, have not added every functionality or every analysis onto the GPU yet. So only certain sources can be created on the GPU. So if you have a special detailed customized source, it cannot yet be created on the GPU, so you can't use the full GPU ray trace. In that case, you have to create the sources on the CPU, like for any FRED calculation. And then once the source rays are created, they're just passed over to the GPU for the fast ray trace and then brought back. So that's the first reason some sources are not available for the GPU yet. The second reason is that the GPU, when you do the calculations on the GPU boards, the GPU boards are very powerful for processing calculations, but it's not very flexible in terms of if you want to do any sort of processing or running a script to look at the ray data yourself, things like that. So you don't have that much power at the end of the ray trace when you want to look at the ray data. So in that case, there are some cases where you want to bring the rays back into RAM as if you've just done a normal FRED ray trace, where you can do your own variety of calculations, or do scripting to look at the rays or save the ray data. When you do the calculation fully on the GPU, the only thing that's returned is the analysis result. So the grid of data for the power calculation at your detector, for example. You don't get any other ray data, except for you can switch on ray path information. You can also look at how much power is absorbed at each surface, but you don't get the specific ray data. So that's the reason. It's sometimes more flexible to do it in the hybrid way.
But then we can say in a general way, we just use the hybrid. This is the safer version, or can we say it?
It's slightly slower because, as you can imagine, creating the source on the CPU is slower than creating it on the GPU, and then also transferring, batches of rays. For the default number is 1 million rays at a time from the CPU to the GPU to do the ray trace and then bring the rays back. There's a little bit of extra calculation time there, so it is a little bit slower. But obviously, still, it's much faster than doing a CPU ray trace because the ray trace is being done on the GPUs. Okay, so a couple of examples. I'll just quickly go through the slides here, and then I'll actually bring up FRED and do this live to talk to you about the examples. So here's a full GPU ray trace example where the source can be created on the GPU, the ray trace is done on the GPU, and then the irradiance at the detector is calculated on the GPU. So in this case, we have a lens system. We got a light source coming in at 26 degrees, and we get some sort of artifact in our irradiance profile. In this particular case, for 100 million rays, the FREDmpc calculation time is about 3 minutes, 200 seconds. And the CPU calculation time on 4 threads, so 4 quad-core CPU, 7.5 hours. So you can see we've gone from 7.5 hours to 3 minutes. And this is just on my laptop here, which is not a high-performance GPU board. So you can see there's some value here. And then another example before I do this live in Fred, is the hybrid example. So here we have an simple illumination application. We have a lawn lamp, and we want to calculate the illumination profile on the ground below. So, for example, if we do the CPU calculation with just 50,000 rays, it only takes 20 seconds, quick and easy. But you can see here that the illumination profile, this is the illuminance calculation, there's not enough data, is there? So you might look at that and say, oh, I need to increase the number of rays by a factor of 100. I need to trace 5 million rays instead. So if I did that on the CPU, it would be 17 seconds times 100. So what's that, 20 minutes, 30 minutes, something like that. That's when the GPU comes in. So if we did the hybrid CPU-GPU ray trace, and we have to use the hybrid because the source is not, in this case, is not suitable for creation on the GPU. So we're using 100 times more rays in the same calculation time, 18 seconds, and I get much, much cleaner illuminance profile. So that's the value there. It helps you reach the accuracy you need in a much quicker calculation time than the CPUs. So let me show you this live in Fred. So first let's do the plastic lens example. So this is the lens system we just looked at. If I wanted to do the general CPU ray trace, let's look and see how long this might take. Obviously, we're not going to wait for 7.5 hours, but we can just get it started, see how we're doing. In the bottom left corner, we're going through like 20,000 rays out of 6 million. That took 11 seconds. We're not even at 1% done yet. Okay, so it's going to take a long time on the CPU. In fact, we're now at 1% after 20 seconds. So let's just stop that. And instead, let's do the GPU ray trace. And we're going to use the full GPU ray trace because the source is set up to be calculated on the GPU. And also, all I want is the irradiance profile on the detector, and my detector entity is already set up to do that. So I click this button. And if you watch the output window, we've just seen the model being loaded, and now it's beginning the ray trace. And you'll see here that it's going to take maybe 15 or 20 seconds for the first line for the first million rays to be ray traced, because there's some preparation that happens. And then we should see each batch of rays happening much quicker. So as you see here with the launch lines, these are the number of rays that are being ray traced. So 1 million at a time. The first time took 20 seconds, and then the next million rays took 2 seconds, the next million rays took 2 seconds, and so on. So every million rays thereafter took approximately 2 seconds on this GPU. And I'll talk about what type of GPU I have later in the presentation. So this took about 30 seconds. Previously on the CPU test, it took us 20 seconds just to get to 1%. So we're almost at a factor of 100. And just to prove that we've actually calculated something, if I look at the analysis results and double click on the detector entity, you can see here I've calculated the irradiance, and there's that's the artifact I was looking for. Now, an interesting thing about this example is that 20 seconds at the start. So this line here. There's some sort of delay there. And that delay is because there is some overhead at the start to prepare the ray trace, to allocate memory to the GPU, things like that, based on the settings of the model. But if I made a change, for example, if I wanted to change the angle of the source, so if I edit my source, and you can see here I'm at 25.999 degrees. Let's change it to 27. Like I'm doing a slightly different angle now. And if I redrew the GPU ray trace, you'll see here that that 20 second doesn't appear anymore. So now it's just at 2.5 seconds, 2.3 seconds, 2.3 seconds, and so on. So once you've loaded the model and done the first ray trace, making small changes such as updating the source or updating the position of a couple of items, so minor changes, removes that initial overhead. So now you can see here forever, when I keep this model open and do a ray trace, we're looking at a ray trace time of 12 to 14 seconds compared to the 30 seconds previously. So FREDmpc is really powerful for doing these sorts of parameter scans if you wanted to loop over a series of source angles, things like that. So we're comparing 14 seconds in this case to what would be about 30 minutes on, well, much faster than the CPU compared, depending on what CPUs you have. You can see here that that's with 6 million rays in this case, in 14.
Tom, a question. I mean, I think that there should be way more rays. Is this true? Because I think on each surface there will be a bounce back. Is this right, or? Yes.
In this case, this is being set up to run in Monte Carlo mode, which means there's no extra rays being created. This is just a simple test of 6 million rays. In the slide I showed you, we used 100 million rays for those times, 200 seconds and 7.5 hours on the CPU. So yes, you'd probably need much more than 6 million rays than this simple example. But in that case, on my GPU, it would just be 2 seconds per million rays. So you can understand how long that would take very simply. It just scales linearly every million rays. So let's do a second example. This is the lawn lamp. So we want to calculate the illumination profile. So first, let me check how many rays I'm using in the source. Okay, just 50,000 rays. If I do the CPU calculation, it's going to take about 20 seconds. And you can see here the bottom left and the little progress bar on the bottom, how long it's taking. And then we'll compare this to using the GPU. So I'll just calculate the irradiance in this case. So you can see here, there's just not enough data. You would not be happy with this calculation result. It's too noisy, not enough rays. So we have to go back. We have to increase the number of rays in our source, let's say by a factor of 100. So I've added 2 zeros there. So now, if I redo the CPU calculation, it's going to take 100 times longer, at a minimum. It'll take even longer if I don't have enough RAM to hold the rays. So let's move over to using the GPU ray trace. So in this case, the rays are being created on the CPU and then passed over to the GPU for ray tracing. And you'll see this in the output window once we get started, how the rays are being moved backwards and forwards. Like the previous example, it's going to take 10-15 seconds just for the first time, just set up the model, and then you should see it chug away.
One question, if you're waiting, Tom, what happens if the CPU is full? Well,
already in Fred and Fred Optimum, if the RAM is full, then it starts writing rays to the hard disk in virtual memory. So it will handle that same case. But that process slows things down. So if you're creating a source with so many rays that you don't have enough RAM, that becomes a slower process. And the same if you bring all the rays back to the CPU to do post-processing, scripting, or something like that. Again, that's just becomes slower if it has to go to the virtual memory on the hard disk. So, I mean, that's another advantage of using the GPUs for ray tracing, is that there's no, because it traces rays in batches of 1 million rays, there's never you don't run out of memory. So there's never any slowdown depending on how many rays you're tracing. So in this case, the first launch took about 20 seconds. And then you can see here we've got some extra lines in the output. Retrieving ray buffer, loading ray buffer. So this is when the rays are passing backwards and forwards between the CPU and the GPU. And you can see here it adds on maybe ½ a second per million rays. You know, so there's a little bit of overhead there. So this took 34 seconds. Again, mostly because of the first time. If we do it again, excuse me, you can see here it probably takes about in total 20 seconds, which is about the same calculation time as we saw in the CPU example. But this time we have 100 times more rays. So a very simple example that we can get us 100 times more rays in the same calculation time. So 16 seconds that took. And just to prove it to ourselves, let's calculate the irradiance on the ground. So the GPUs allowed us to get a much smoother plot in the same calculation time.
I mean, I know from the basics of the calculation of rays. I mean, there's the Monte Carlo method, the non. I mean, there are different modes. Is this possible with MPC, or is do you have to pay an update or an upgrade for this to do?
No. In FREDmpc, you can trace either using Monte Carlo or what we call ray splitting. The default settings in Fred is actually ray splitting, where when a ray comes into a surface and there's a transmission and reflection coefficient and or scattering, multiple rays are created to generate each component. So that is also possible in the GPU, or you could switch to using Monte Carlo, depending on the situation. It's your choice. So the GPU ray trace can handle both of those techniques.
This means like sequential and non-sequential, both is possible with MPC.
Well, in both cases, we're talking about non-sequential.
Okay.
Yeah, FREDmpc doesn't do any sequential ray tracing because it's usually unnecessary to trace billions of rays in sequential. So it's just never been written for FREDmpc. So in both cases, Monte Carlo and ray splitting, it is non-sequential.
Okay.
It just means that in Monte Carlo, that the number of rays does not increase during the ray trace, so it's easier to handle or predict calculation times and statistics. That's the reason. But there are times when you want to use one over the other, and that's the same for all ray tracing as well, and for the CPU as well. Okay. So just let's quickly talk about what we saw then, what Fred was doing when we did those GPU ray traces. So the first thing, when you click the button to do the GPU ray trace, the GPU device itself needs to be initialized. This means it has to be prepared to do a calculation. We have to allocate a chunk of memory to hold the ray data and things like that. And then the next step is actually loading the Fred model. The Fred model is not dynamically updated on the GPU. So when we click the calculation button, that's when the model is being moved to the GPU. So there's a GPU version on the GPU. When you make changes to it later on, it's not a full load again. It's just it loads the updated piece. But that happens automatically when you click the ray trace, the GPU ray trace button. So that's the overhead. Oh, well, there's a third one as well, ray trace preparation. This is when the GPU code is being compiled and optimized for ray tracing. This could take 20 seconds, 30 seconds, 40 seconds, depending on the GPU board being used. And this only occurs the first time the model is loaded onto for a ray trace on the GPUs. So these are all overhead that takes place before you do the calculation on the GPU. And then during the calculation, depending on which option we have, and we saw this in the both examples I just showed you, if we're doing the full GPU ray trace, the ray creation of the source is on the GPUs. This is obviously much faster than creating it on the CPUs. However, only specific source configurations allow rays to be generated on GPUs at the moment. It's just at the moment. The development team are just moving each, updating sources. It just takes time to do each source type available for the GPU, but it's just currently only some sources can be created directly on the GPUs. If we're doing the hybrid ray trace, the rays are created on the CPU as it was in the CPU calculation of FRED, and then chunks of rays are copied between the CPU ray buffer and the GPU device for ray tracing. So we saw those lines in the output window for 1 million rays or so each time. That's the chunks that are being moved and ray traced at a time. It's a little bit slower, but there are no restrictions on the type of source that you can use. And then for the ray trace and analyses directly, if you're using the full GPU ray trace, then whatever detector entities and directional analysis entities you have set up in your model will generate these analysis results nodes in the analysis results folder at the end of the GPU ray trace. So that's what you receive back from the full GPU calculation, is the analysis results. One key point, though, is that the ray data is always confined to the GPUs. So you never get, if you're doing the full GPU ray trace, you never see the ray data itself. It's all done and it cannot be accessed for your own diagnostics or scripting or saving the ray data to file. You can't do any of that. It's untouchable, if you will. However, in the hybrid case, after the GPU ray trace is completed, the ray data is moved back into the CPU ray buffer, allowing you to save the ray data or do other types of analyses or running scripts to do your own diagnostics, things like that. So there's more flexibility for post-processing in the hybrid ray trace. And that will probably remain the case for a few versions forward, because the GPU board is not designed to hold many gigabytes of ray data for you to access and manipulate. So that's a difficult problem to solve with GPU ray tracing. So here's a summary of pros and cons for the two GPU ray trace versions. The full GPU ray trace is the fastest, and your RAM and hard disk space is not used for the ray trace. So you don't have to worry about having enough RAM for the calculation or enough hard disk space to write the ray data to the hard disk. These are key points. The con, so the negative parts of the full GPU ray trace, is that not all source types can be used currently. This will be probably changed in the next few versions coming forward. And also no customized post-processing is allowed. All the rays remain on the GPU and cannot be accessed by the user. The hybrid is more flexible. All source types can be used. And at the end of the ray trace, all the rays are in memory, available for any post-processing or other analyses. However, it's slower than the full GPU ray trace, and you need to have enough RAM and disk space to hold the rays at the start and the end of the ray trace. Okay, and this matters if we're talking about billions of rays, because a billion rays is 200 gigabytes of RAM, for example. So you need to be careful. Another key point, which I haven't mentioned yet, is that if we're doing the ray splitting mode in the hybrid method, the child ray data that's created during the ray trace on the GPUs, the child rays are created on the GPUs and are traced through the system, but those child rays currently are not brought back to the CPU. So if you brought the rays back to the CPU in the hybrid ray trace and then did post-processing, it wouldn't have any of the child ray data. So this is a key point. Like if you're doing, and child rays data is normally like scattered rays, things like that. So you have to be a little bit careful here, and that's why in many cases it's more suitable to use the Monte Carlo method if you're using the hybrid ray trace. Because in the Monte Carlo method, there's no such thing as child rays. You start with a certain number of rays at the beginning of the calculation, and you end up with exactly the same number. No rays are created dynamically in the Monte Carlo ray trace.
Maybe can you explain the difference between Monte Carlo ray trace and non-sequential ray trace?
Okay, yeah, so both are non-sequential, but what happens is Monte Carlo, we don't create rays. When a ray hits a surface with a transmission reflection component, for example, we don't create two rays coming out, one for transmission, one reflection. That same ray, during the calculation, is decided to be transmission or reflection, and that's decided based on probability, hence the name Monte Carlo, like the casino. So if, for example, the transmission component is 99% and the reflection component is 1%, then on average, every 100 rays that come in, 99 will be transmission and 1 will be reflection. So it's just based on probability, but no rays are created. So that one ray does not create child rays. And whether it becomes a transmission or reflection component is just based on the probability based on the power values of each component. So that's sometimes a very convenient method to use. The downside to using that, using Monte Carlo, is if you have, for example, an anti-reflection coating on a lens surface with a reflection component of 0.1% or 0.01%. So 0.01% means you only get one reflection ray every 10,000 rays that hit the surface. So in those, when we're talking about very small power values, it's difficult to get enough rays for accurate statistics if that reflection is key for your stray light analysis, for example. So that's the downside with Monte Carlo. But technically both are non-sequential ray tracers. So in the live example I did when I used FRED a few minutes ago, we saw about approximately 100 times faster than my 4-threaded CPU. But what type of GPU board do I have? Well, I have a GeForce GTX 950. So this graph, this is available on the Photon Engineering website. This compares many GPU boards that have been tested by Photon Engineering and also some FRED users through a series of benchmark calculations. In this example, this shows the relative speed of each GPU. And we've used the GTX 1050 Ti as the reference point. So you can see here that goes up to 1. And then we're comparing the speed of all the GPUs relative to that. My GPU was slightly under that at 950. So between this 750 and 950. So let's just assume I'm roundabout here. So I was seeing on those two examples a factor of about 100 speed increase. So if we had a 1050 Ti, we would see approximately the same. But you can see here on a variety, as we go up through the various GPU boards, how the speed, relative speed increases. Now the width of this bar here shows you there's a huge variety in the types of simulations. I don't know the details, but it might be a case where large amounts of scatter might be more efficient or less efficient, or large models, smaller models, things like that. There's a whole range of calculations we did and compared. But you can see here that if we go up towards the top, we're looking at, if my calculation was 100 times faster, if I had, for example, the Titan 5 GPU board, you could say I'd be 500 times faster, or, well, let's take the middle, 800 times faster. You know, so there's a lot of power. When we say FREDmpc is 100 times faster or 500 times faster, that's a ballpark figure because it depends on so many variables. It depends on the model. It depends on what I'm comparing it to. So I'm comparing it to 4 CPUs, but many people have 8 or 16. You know, so these are all ballpark figures, but you can see here that if I just plugged in one of these GPUs instead of mine, I would have seen a much faster calculation. The board that we recommend is the RTX. Because it's the new generation of NVIDIA board, there's 2 reasons why we recommend it. One, very good cost performance, and you might not be able to see it, but out here the US dollar price in America, it's just over $1,000, and it's got a really good performance. So 1,000 euros or so, I'm not too sure. So very good cost performance. And also, this is the new generation of NVIDIA board. And as the software libraries are updated, the FREDmpc calculation will become even faster without the programmers having to redo the code or anything like that. So immediately there'll be a small jump in speed increase as this becomes more, as the libraries become updated. So that was just comparing one GPU board, but one key thing which we touched upon at the beginning of this conversation was you can use multiple GPU boards without limit. So you can have, if I go back, if you have a workstation with 2 of these RTX boards plugged in, you can double these numbers. And there's no inefficiency, it's not like a curve, you know, straight up. 2 means twice as fast, 3 means 3 times faster, because it's such a parallel calculation. So calculation speed scales linearly with the number of GPU cores. And a really nice feature about GPUs is that they're advancing very quickly, much quicker than advances in CPU processing speed, you know. So this year there are GPU boards with a few hundred cores. Next year there'll be ones with a few thousands and so on. It's really, speed will just increase really very quickly over the coming years. And again, touched upon earlier in the course, sorry, in the presentation, you can also run the calculation in the distributed setup as a cluster. So we can have multiple workstations, each with 2 or 3 GPU boards inside it, and you can do the calculation that way. So technically, there is no limit on how fast you can do these calculations. It all depends on the hardware that you have available. But FREDmpc lets you expand it however you can. Okay, so now a couple of points to bring us a little bit back down to earth. There are some current limitations in the current version of FREDmpc. As I said at the start, every feature in Fred needs to be rewritten into the GPU code. And basically what that meant was there was a huge to-do list for the development team. You know, translate this source type, translate this source type, include scatter effects, include volume scatter, include so on, right? So the first release of FREDmpc last year was just a starting point. It had the core features needed for stray light analysis, such as it includes scattering, child rays, ray splitting, ghosting, multiple source types, calculating irradiance, all of that key features for a majority of calculations. But here are some features that are not yet implemented and will be coming in the coming versions of Fred. First of all, numerical precision. The GPU ray trace is currently only a single precision, while the CPU ray trace is double precision, meaning that if you had models with long propagation distances or many, many intersections, small errors might start to accumulate compared to the double precision ray tracing. This is only really, really critical if you need to have accurate optical path length data and things like that. Or we're talking about optical surfaces that you need very high accuracy intersection points. But that's something that will be switched over in the coming versions of Fred. Secondly, not all Fred geometry has exact GPU implementation. So the programmers had to translate every surface profile that they could into GPU code, and they haven't done it for all surface types yet. In those cases where it's complicated geometry, Fred will use a triangular mesh to represent the GPU structure, the structure on the GPUs. So in many cases that's fine if it's just a housing surface or something like that. But there are some cases where that's the case, and it's just something to be careful for. But again, these are things that will be checked off the to-do list going forward. 2 key things that are not yet available in the GPUs are coherent propagation. So FREDmpc does not support coherent ray tracing. So one of Fred's strengths is that it can calculate the coherent beam going through a system, so it can calculate diffraction, interference, coupling to a fiber, wavefront analysis, things like that. That's not yet available on FREDmpc. And the same for polarization. FREDmpc does not support any polarization ray data. These are things that have been requested by many FREDmpc users, so they're quite high on the to-do list for the next development, but currently that's not available. In regards to ray trace paths, the ray trace path data can be tracked on a FREDmpc calculation, but things like filtering the rays based on which ray path they're on, or redrawing ray history for a specific ray path is not yet available. And then finally, scripting. So in FRED, you can create a surface profile using a script, or material or scatter model using a script. These are not supported on FRED yet, because those versions required FRED to run the script dynamically whenever a ray hit the surface or went through that material. Those scripts cannot yet be run on the GPUs. So just some limitations which will be knocked off as we go forward in future versions of FREDmpc. However, speaking of coherent propagation, which is not yet available, there is something that is available for users who do use coherent propagation. So if you do the calculation on the CPU, the coherent ray trace, the next step is to calculate the coherent irradiance, for example. That process, if you have many, many rays or many pixels, can sometimes take a few minutes, maybe an hour or two, depending on how many rays we're talking about. That part of the calculation is now available to be done on the GPU. So you do the ray trace on the CPU, but then before you click the irradiance button, we select the option to do the coherent sum on MPC using the GPU, and you can do the irradiance calculation, that part of it, much, much faster. So we're talking about, on average, about an order of magnitude, so about 10 times faster than the CPU irradiance calculation. And that helps. So instead of something that might take an hour, it might take 6 minutes or 10 minutes or something. So there is some value there if your priority is coherent ray tracing. The ray trace itself is not yet available, but the coherent summation is. So the note at the bottom is just saying I was wrong earlier when I said the only difference for the FREDmpc GUI is 3 new buttons. Well, there's actually 5 because we have these 2 here as well. So that was a new feature in the most recent version of FRED, version 1940. And then finally, just to finish off this presentation, just a couple more examples, just to show you what FRED can do. On the left here, we have a ray trace result of 1 billion rays, calculating the irradiance distribution on the housing of a lens when we have a light source, a solar illumination at 20 degrees off axis. This includes ghosting between the lens surfaces and scattering of the housing. 1 billion rays on a GTX 1080 Ti GPU board, and this took about 13 minutes, 14 minutes for 1 billion rays. Again, if I had 2 of those boards, we would halve the time. And then this is a really nice example. This is 10 million rays, and we have 2 sources. We have a bitmap source, which is taken from a camera of this is actually a real scene of flowers. And then we have a solar source coming in at a certain angle above to create the flare. So we have 2 sources, total of 10 billion rays in FREDmpc. Took about 2 hours for 10 billion rays. You can see here we got a nice ghosting effect with the multi-wavelength and multicolored flare. So you can really do these types of analyses in not too long a calculation time. For example, this 10 billion rays might take, if we weren't using FREDmpc, might take 3 or 4 days. Whereas 2 hours, that's just a long lunch. So there's a lot of value in being able to do these type of accurate calculations in this relatively short amount of time. So that's my presentation. I hope it was useful for understanding FREDmpc. One thing I want to mention is, if you're interested, if you have a copy of FRED or FRED Optimum right now, and you want to test FREDmpc, just let us know. We can, all we need to do is just send you, ask my colleagues at Photon Engineering to send you some updated codes. You can run FREDmpc for a month. You don't have to download any new version of the software. You just plug in the codes into the Fred license authorization interface, and then you can test FREDmpc, see how fast it is, how suitable it is for your needs. So we can do that straight away. So just let us know, contact me or Axel through the website or by email, and we can set that up for you.
Tom, I want to pick a question here.
Sure.
One question, how is the price, the license model, is this different to Optimum or the standard version of Fred? Can you explain?
Yeah, I guess we should clarify that. So FREDmpc is a higher version than Fred Optimum. So with the release of FREDmpc, it became the third version. So we have Fred, or Fred Standard, if you will, Fred Optimum, FREDmpc. And there's a small incremental cost if you want to jump from Fred Optimum to FREDmpc, for example.
Is this a rental? Is this a rental fee, or how is this working?
No,
every time is renting, and it costs each year a lot of money. And if you don't spend the money, how is this solved with Fred? Yeah,
so Fred typically does not do an annual rental or annual lease. So you'd be upgrading the version of the software. So it'll be an initial cost of a few €1,000 to jump from Fred Optimum to FREDmpc, and then the annual support every year thereafter will jump up by a couple of €100 just for the higher version. So it's just an initial cost at the start, really.
Okay. I see in the past that Fred and Photo Engineering and CBS Europe really like students and all the education stuff. What is this also available for FREDmpc?
Yes, yeah, that's right. We offer student licenses for students. They can have a free license of Fred for a semester tied to their computer, and that can be a FREDmpc. Yeah. Okay,
the demo version cost us something? Is this does this need some cost? There are some costs involved for 1 month of testing?
No. So there are two versions of demo. There are two demo versions. One is actually called the demo version, which you can download from the website, which has no time limit, but you can only trace a very small number of rays. I think it's 500 rays. And that version is just for you to get a feel for the software user interface, to look at the help, to really just get a feel for it at the start. And then if you wanted to test the software more rigorously, a 1 month free trial is available, and that is FREDmpc.
Oh.
And obviously free, yeah.
Great, thanks Tom for all your help, your great presentation.
You're welcome, Axel, and thank you for your time. And to everyone listening, thank you. And so thank you. Get in touch if you have any questions, and we didn't answer them through the chat. We can connect again. If you wanted to talk specifically about using FREDmpc for your models or your work, we can set up a one-to-one webinar and talk in more details about what you need from FREDmpc. And I look forward to working with you soon. Okay. Thank you. Goodbye.
Thanks. Bye-bye.